Hello, I'm SA, your AI essayist. Please note that all content, audio and video in this presentation are AI generated. As AI can sometimes produce inaccuracies, I encourage you to verify any factual information presented. With that in mind, let's begin.
Edward Norton Lorenz 1967 paper, The Nature of Weather Prediction, stands as a watershed moment in the history of science, fundamentally altering our understanding of predictability and chaos. It transcends a mere discussion of meteorological forecasting. It delves into the very fabric of deterministic systems and exposes the inherent limitations in predicting their long-term behavior. A thorough examination of Lorenz's work necessitates an appreciation of the intellectual climate preceding its publication, the specific methodologies he employed, the immediate and subsequent impacts of his findings, and the criticisms and revisions that prior to Lorenz's groundbreaking contribution, the prevailing scientific worldview, particularly within physics and related fields, leaned toward a deterministic perspective. The clockwork universe, a concept popularized by figures like Pierre Simon Laplace, suggested that knowing the initial conditions of a system with sufficient precision would enable perfect prediction of its future states. Weather forecasting, while empirically challenging, was viewed through this lens. The difficulty lay primarily in gathering enough data and possessing adequate computational power, not in any inherent unpredictability in the system itself. Numerical weather prediction, pioneered by Lewis Fry Richardson in the early 20th century, aimed to solve the equations governing atmospheric flow, albeit with limited practical success given the computational constraints of the time. These early attempts, however, reinforced the belief that improvements in data collection and computational techniques would inevitably lead to more accurate and extended weather forecasts. Lorenz's work arose from his efforts to build a simplified computer model of atmospheric convection. In 1961, while experimenting with this model, he observed an extraordinary phenomenon. He started a simulation using initial conditions that were ever so subtly different, representing a rounding of numbers from 6 decimal places to 3. He expected the subsequent weather patterns to closely mirror the original run. Instead, the two simulations diverged dramatically, rendering any long-term correspondence practically non-existent. This seemingly innocuous observation held profound implications. It demonstrated that even in a deterministic system governed by well-defined equations, extreme sensitivity to initial conditions could lead to unpredictable behavior. Minute variations, well within the realm of measurement error, could amplify exponentially over time, completely altering the trajectory of the system. The mathematical model Lorenz employed, consisting of a set of 3 coupled, nonlinear ordinary differential equations, is central to understanding his findings. These equations, derived as a drastically simplified representation of the equations governing fluid convection, are expressed as dx dt equals sigma times quantity y minus x, dy dt equals x times quantity rho minus z minus y, and dz dt equals xy minus beta z, where x is related to the intensity of the convective motion, y to the temperature difference between ascending and descending currents, and z to the distortion of the vertical temperature profile from linearity. Sigma represents the Prandtl number, rho represents a parameter proportional to the Rayleigh number, and beta is a geometric factor. While these equations are deceptively simple in appearance, their solutions exhibit remarkably complex behavior. For certain parameter values, the solutions trace out a distinctive butterfly-shaped attractor in phase space, now famously known as the Lorentz attractor. Trajectories on this attractor are chaotic, meaning they are bounded but never repeat, and exhibit sensitive dependence on initial conditions. Lorenz's 1967 paper meticulously documented this sensitivity. He demonstrated that even arbitrarily small errors in the initial state of his model would grow exponentially, rendering long-term predictions impossible. This concept, he termed deterministic non-periodic flow, challenged the prevailing notion of predictability in science and engineering. The implication was clear: weather, being a complex dynamical system, was inherently unpredictable beyond a certain time horizon, regardless of how precisely the initial conditions are known. This discovery, which would later become popularized as the butterfly effect, wherein the flap of a butterfly's wings in Brazil could theoretically set off a tornado in Texas, had a transformative impact on the field of meteorology and beyond. The immediate impact of Lorenz's work was met with a mixture of skepticism and excitement. Some meteorologists, wedded to the deterministic paradigm, initially resisted the idea that weather prediction had fundamental limits. Concerns were raised about the simplicity of Lorenz's model and its applicability to the real atmosphere, a system of vastly greater complexity, with a multitude of interacting variables. However, as computational power increased and more sophisticated models were developed, the limitations of predictability became increasingly apparent. Lorenz's work provided a theoretical framework for understanding why forecast accuracy inevitably degrades over time, even with improved data assimilation and numerical techniques. Beyond meteorology, Lorenz's findings resonated deeply within other scientific disciplines. It laid the foundation for the development of chaos theory, a field that explores the behavior of complex, nonlinear dynamical systems. Chaos theory has found applications in diverse areas, including fluid dynamics, population biology, economics, and even social sciences. The concept of sensitive dependence on initial conditions has become a fundamental principle in understanding the behavior of many complex systems, challenging the traditional reductionist approach that seeks to decompose systems into simpler, predictable components. One of the key contributions of Lorenz's work lies in its emphasis on the importance of nonlinearity in determining system behavior. Linear systems, which are characterized by proportionality between cause and effect, are generally predictable. Small changes in initial conditions lead to small changes in the outcome. Nonlinear systems, on the other hand, can exhibit disproportionate responses to small perturbations. This nonlinearity, coupled with feedback mechanisms, is what gives rise to chaotic dynamics. Lorentz equations, while simple, capture the essence of this nonlinearity and demonstrate its profound consequences for predictability. Lorentz's work prompted a re-evaluation of forecasting methodologies. It became clear that pursuing ever-increasing precision in initial conditions would yield diminishing returns beyond a certain point. The focus shifted toward ensemble forecasting, a technique that involves running multiple simulations with slightly different initial conditions and model parameters. This approach acknowledges the inherent uncertainty in the system and provides a probabilistic forecast rather than a single deterministic prediction. Ensemble forecasting has become a standard practice in operational weather forecasting and has significantly improved the reliability and usefulness of weather predictions. The reception of Lorentz's work underwent a significant transformation over time. Initially met with some resistance, it gradually gained acceptance as the implications of his findings became more widely understood. His 1967 paper is now recognized as a seminal work in the history of science, cited extensively across numerous disciplines. Lorentz himself became a highly respected figure, receiving numerous awards and accolades for his contributions to meteorology and chaos theory. Critiques of Lorentz's work primarily centered on the limitations of his simplified model, the three-equation system, while capturing the essence of chaotic behavior, a highly idealized representation of the atmosphere. It neglects many important physical processes, such as radiative transfer, cloud microphysics, and land surface interactions. Furthermore, the parameter values used by Lorentz were chosen to maximize the chaotic behavior of the system and may not be representative of the actual atmosphere. Later researchers focused on developing more comprehensive and realistic models that incorporate a wider range of physical processes and parameter values. These models exhibit chaotic behavior as well, but their predictability limits may differ from those predicted by Lorentz's original model. The influence of prior works on Lorentz research is evident in his familiarity with the field of fluid dynamics and the early attempts at numerical weather prediction. He drew inspiration from the work of meteorologists like Carl Gustav Rossby, who had pioneered the study of atmospheric waves and the general circulation of the atmosphere. Lorentz's simplification of the governing equations to a manageable set of three differential equations reflects a deep understanding of the essential dynamics of fluid convection. Lorentz's work, in turn, profoundly influenced numerous researchers and fields. Mitchell Feigenbaum, for example, was inspired by Lorentz's work to investigate universality in chaotic systems, leading to the discovery of the Feigenbaum constants, which characterize the period doubling route to chaos. David Vieul and Floris Takens used Lorentz's ideas to propose a new theory of turbulence, suggesting that turbulence arises from the presence of strange attractors in the fluid flow. Edward Ott, Celso Grabogi, and James York developed the OGY method for controlling chaos, a technique that allows one to stabilize unstable periodic orbits in chaotic systems. In conclusion, Edward Norton Lorenz 1967 paper, The Nature of Weather Prediction, represents a paradigm shift in our understanding of predictability and chaos. It demonstrated that even in deterministic systems, extreme sensitivity to initial conditions can lead to unpredictable behavior, fundamentally altering our view of weather forecasting and complex systems in general. Though simplified, its elegance lies in distilling profound complexity into mathematical forms. Initial resistance gave way to widespread acceptance. Lorentz's legacy endures, influencing countless researchers and shaping our understanding of the intricate dance of order and disorder in the natural world. The butterfly effect, once a disconcerting idea, now serves as a potent reminder of the interconnectedness and inherent limitations in our quest to predict the future.
We really appreciate you tuning into this AI-powered presentation. Our goal is to push the boundaries of AI in content creation, and your input is invaluable. If there's a particular subject you'd like to see us tackle next, or if you have suggestions on how we could fine-tune our AI's creative prompts, please don't hesitate to leave your ideas in the comments section. We're excited to bring you more unique content very soon.